All right. Hello, everyone, and welcome to part 3 of our 4-part Graph Guru series on setting up a patent graph within TigerGraph. If you recall from our last session, we designed the schema of our graph based off of the data files that we're going to be building it based off of. And today we'll be taking a look at how we go from that schema that we sort of designed outside of TigerGraph, bring that into TigerGraph, and then additionally bring in our data and map that to our graph and get it loaded in as well. So like with last time, we have a link which you can also find in the chat for the webinar, which has goes out to a link sheet with a bunch of additional links on it for anything that you might need or might want during this presentation. So we will be following along with the Jupyter notebook that is in the repo for this project. And additionally, we'll be using a TigerGraph Cloud instance. So if you'd like to follow along, you can go ahead and spin up a blank TigerGraph Cloud instance now, and it should be ready by the time we start getting into things. So first things first, just some housekeeping items. This is being recorded for everyone to be able to view later on. If you have any questions, feel free to submit them through the Q&A panel at any time. There will be a few natural breaks that just kind of come up in this presentation, so I'll be trying to answer questions during those breaks, but feel free to submit them anytime and I will get to them when I can. And additionally, if you have any issues with the Zoom or if you need things to be bigger on the screen, then feel free to just kind of ping that in the chat as well, and I'll make adjustments accordingly. So with that said, let's jump right into it. Like I said earlier, the goal of today is to take the schema that we designed last session, integrate that into TigerGraph, and then populate it with our data. So as a refresher, this is the schema that we built out in the last session. It's nice and complex, and there is a lot of it. It fully models our whole graph and all of the 9 different data files or 12 different data files that we had pulled in. Hold on 1 second, let me just drop that link back in the chat again. And there you are. Okay. So looking at this, there's actually some changes that I want to make. Not big changes, but just something that I noticed looking back at it and seeing a way that we can improve this schema just with something I personally didn't know before about TigerGraph and something that we'll be taking advantage of with this. So if we look at the upper left region of our graph, which was kind of that the area which corresponds to the locations, what we'll see is that in our initial schema, we had a bunch of these edges that were unique. So for example, correspondence in city, correspondence in region, address in region, code in region. All of these edges, while they do have different names, represent more or less the same thing. They represent a geographical hierarchy. You know, city is within a region, postal code is within a city, and so on and so forth. So because of that, we don't really need each one of those edges to be a unique name. So this is something I didn't know before, but we can have edges that have the same name, but go between multiple different vertices. So if we look at this image on the right, we can see now that we've adjusted no longer correspondence in city, but we just have an in city edge. And the same with our address in city, and these region edges as well. We no longer need to have these unique edge types for every situation where we are trying to express what is essentially the same relationship. So these are called compound edges, and we'll get into how we actually create them when we load things into TigerGraph and how that looks a little bit different from any of our regular edges. We'll get into that, trust me, but I'm just want to express that these exist and they do allow us to clean up some of our schema. But one thing you'll notice is that while we are using compound edges to express, for example, correspondence in city, address in city, we're not using it for inventor. And that's because for these other situations, like I said, we're representing a geographical hierarchy. We are talking about one space and how it fits within another space. But our inventor isn't a space, you know, so it's not the same relationship there. It's not this hierarchy of locations. it is a person who was in a location at the time that the patent was filed. So it's a different type of relationship. It's a completely different concept that's being represented. And because of that, we want to use a unique edge type for that concept. So this just kind of goes along with what was talked about in the last session of how we want to really be modeling concepts when we create our schema. So in areas like this, when we have the ability to combine a few of those concepts into similar edge types, we want to do that, but we want to make sure we're not overusing that and we're not bringing in things that aren't necessarily exactly the same concept when we create these compound edges. So because of that, this region of our graph will look slightly different than it did in the full schema, just because we will be using those compound edge types. So the next thing to get into is for everything that we'll be touching on in this presentation, there are two ways of doing it. So the first one is through the Graph Studio visual interface, which is kind of what you've seen during that first session where we sort of clicked around and set up that sample graph in there. And then additionally, we're going to be going through how to do it via GSQL code as well. So GSQL is TigerGraph's native querying and coding language. And essentially everything that you do via Graph Studio gets turned into GSQL code, which gets executed on your TigerGraph server. So while these are two separate interfaces for doing the same tasks, at the end of the day, under the hood, they're both doing exactly the same thing and interfacing with the TigerGraph solution in GSQL, in the GSQL language. So because of that, obviously the interface provides a lot of visuals and the ability to quickly see all of the options that you have. You have a drop down to see all of the variable types. You have drop downs to see the different types of edges that you can create. You have an easy interface to add attributes and things like that. But for a use case where you'd like to be able to programmatically spin up a graph or to be able to deploy something online, you don't really want to have to click through that interface every time. So therefore, having it in code allows you to just execute that code, and that can then create your schema or load in your data or whatever it is that you're trying to do with your GSQL. So these are just kind of some of the different features that each one of these interfaces offer. Like I said, Graph Studio is personally, when I am first setting up a graph, I do everything in Graph Studio. It's just easier for me to visually see things as they're being connected, to be able to link things together and do that. And in addition, anything that you do in Graph Studio, there's a nice little export button that will export all of that as GSQL for you. So there's no real limitation to doing it in Graph Studio as far as it not being, redeployable or any of that. There's that nice handy export solution, which will give you the GSQL representing what you just created through the visual interface. So personally, I like to start there just because it's easier. And then eventually I transition into GSQL code as I need to be able to spin up, spin down that solution or make changes from outside of the Graph Studio interface. Now, another thing I want to talk about before we get into creating our schema is that something that we touched upon a little bit in the first session is the difference between global schema and graph schema. So when we work with TigerGraph, is there an import for GSQL back into Graph Studio? There is. So you can export a solution on one box, import it on another box completely seamlessly. So there's kind of these two schemas within our TigerGraph solution. So remember, I'm going to be using TigerGraph solution here. Solution here is more or less the TigerGraph instance running on the server, and that can contain multiple graphs. So solution is the broader topic. Graphs are within the solution. So a global schema applies to the entirety of the solution. A graph schema only applies to one of the graphs within that solution. For today's demo and most of the graphs that end up being created, we're only working with one graph within one solution. So in a way, these schemas are interchangeable. However, it's best practice to be designing as if you might have multiple graphs. So we'll just want to take a look at how we'll set up those different schemas and some of the advantages and disadvantages to doing it either way. So like I said, the global schema exists on the solution, and you can pull as much or as little from the global schema as you want into any of your graph schemas. So if you have a global schema with a bunch of vertices in it, you only care about 3 of them in one particular graph. That's all you need to bring in. If you don't care about any of them, you don't have to bring in any of them. If you want to just duplicate that global schema within your graph, you can do that as well. So there's plenty of options there as far as global and graph schema goes. But there are some caveats. If you have a global schema and you've imported some of that into a graph, and you then want to make a change to that global schema, then any of those vertices or edges that you are looking to change will need to be first dropped from any graphs that use them. They will need to be changed on the global level and then brought back into the graphs that use them. So by doing that, it kind of creates this extra process where you have to drop and then re-add those components to the schema. But what this does do is it does maintain that they will be consistent across all of your graphs. So if you're using the global schema as intended and you have a vertex type that you want to be replicated across all of your graphs, then it makes sense that any updates you make to it on a global level should have to propagate down to all of your graphs. And just because of that process, you do have to drop and then re-add those to your schema. Versus when you're within a graph itself and you want to modify the schema. So this is for an element of the schema that only exists within the context of the graph, then you can just edit that. It may cause you to have to unload some of the data that is attached to, say you're modifying a vertex, you may have to unload the data from that vertex if you're, say, removing an attribute. But in other cases, you can modify that schema. Say you're adding an attribute and the data will remain in place. It obviously won't have values for the new attribute. You would have to reload your data in order to add in those additional values. But it does make it a little bit easier to modify your schema. And because of that, that's what we'll be doing. We're going to take approach for each one of these for our different solutions, just based on sort of what is easier and to kind of show the process that comes from doing it through each of these ways. Is the data unique for a global vertex type? Yes, so the data is on a graph level. Your schema is just the representation of how that data will be arranged, but the data itself is on a graph level. So let's see. Another thing I want to talk about really quickly is we have 3 main features of our graph. We have vertices, we have edges, and we have attributes. In something like the complex graph that we have here, that's a lot to take in. We have a lot of vertices, a lot of edges, and a lot of those vertices have multiple attributes. So eventually, when we go to query a graph, we want to be able to tell apart what we're talking about. Is this the inventor vertex, or is this some attribute called inventor? There's no easy way to do that without having some sort of distinct naming convention across each one of these components of the graph. So I've shown here the naming convention that I personally use and what I'll be using for this demo. Obviously, pick what works for you, but I'll just briefly touch on this. So for vertexes, I use Pascal case, which means that it's no spaces between words, and each word, including the first one, has a capital letter. So you can see some examples there of some of the vertex types that we'll be creating for this demo. Additionally, edges, snake case, this just lowercase with an underscore between the words, just allows you to easily see that that's an edge. And attributes, I use camel case. So it looks somewhat similar to Pascal case, but you can tell that it's an attribute because the first letter is not capitalized. So that's just what I'll be using for this. Obviously, pick whatever naming conventions work best for you, but for the purpose of this demo, that's what I will be using. So let's jump right into things. We'll hop into the Graph Studio schema design. This was touched on a little bit in that first video, the intro where we set up that graph, but I'll be going into a little bit more detail on some of the things that we can do there. So in order to do this, we are going to hop into our TigerGraph solution. So I have one set up here. If you have another one set up, you can just log into that. And we're going to be creating this schema in the graph workspace. So we're not going to be creating a global schema. So in order to create a schema within a graph, we first need a graph. So I'm going to select on this global view up here, click create graph, click create graph, and I'm going to call it patents. And we're going to go ahead and click create. And that's just going to take a second to spin up the actual graph. Inconsistencies. So how to handle potential inconsistencies between global and graph schema. The graph schema will take precedence. So if you modify, you cannot modify a global schema element from a graph schema. It's part of the global schema. It's in the global schema. If you want to modify that within a particular graph, then you would need to modify that at the global level, or you would need to drop that from the graph and create a graph specific vertex that has the, or edge that has the fields that you're looking to change. But in general, if you have one element that's used across all of your graphs, that should be within your global schema, and it doesn't really make sense to have a bunch of slightly different variations of that same element across all of your graphs. So spinning up a graph will just take a second, but once that's done, we'll be able to see that this global view up here will switch over to our graph view. We'll say patents. And then from there, we can go ahead and start clicking around to create our first vertices and edges. I'm not going to do the whole schema through this. I'm obviously just going to show enough to express the different things, because doing the whole schema would take a long time clicking around, and that's the advantage of the GSQL code that we have. So we're just going to wait a second for that. There we are. So now if we click up here, we can select patents. We can go to design schema, and we'll see that we have a blank schema. There we are. So to create a vertex, we just go up here and select add local vertex type. And for this one, we are going to be using the, which one is it? We'll just use the application vertex. So we'll call it application. That's our vertex name. Application. So this is the vertex type name. When we reference vertices of this type, they will be application vertices. Primary ID is the primary ID of the vertex. This has to be unique for each vertex of any given type. So if I have application 1, I can't have another vertex that is application 1, but I could have another vertex that is patent 1. So they can both have the same primary ID as long as they're not the same type of vertex or edge. So for this, we'll just be using ID as our primary ID, and we'll have that as a type of string. Additionally, this as attribute box here, normally you cannot access the primary ID when you're querying it. So if you want to be able to query a vertex and be able to interact with that vertices ID, then you will need to add it as an attribute as well. The style section here is really purely just for the Graph Studio interface, but allows you to change what that vertex looks like within the interface. And lastly, we have the ability to add attributes. So these attributes allow us to specify an attribute name. So we could have something like title for this one, and we can select the type that that is as well. Additionally, there's this box here for index. So you can only one attribute per vertex can be an index, but this is not required. So if you have another attribute that you want to index on for faster lookup, then you can select that index checkbox, and that will index that attribute. So that way you can gain a little bit of performance when accessing that later down the line. Additionally, there's this field here for default value. There is no such thing as a null in TigerGraph. Everything has to have some value. So if I go to load in data into this application vertex and I don't have data for the title, then it's going to assume this default value. And you can view those default values in our documentation, but for a string, it is an empty string. So we'll go ahead, we'll add this basic vertex in here, and we'll add another one as well for inventor. And we'll do something similar here where we give them an ID. And for our inventor, we have first name, middle name, last name. We have a bunch of other things. I'm not going to put the most effort into getting these exactly right, since we will be loading in our schema through code in a little bit. I'm just here to show the process of what this looks like setting this up. So we can go ahead and do that, add those additional attributes as well, and click add. So now we have 2 vertices in our schema, and we need to create an edge between them. And we can do that with this add local edge type button up here. And we click our source vertex, and we click our destination vertex, and that creates an edge between them. And we'll call this one has inventor. So now we have this option where we can select directed if we want this to be a directed edge. For the use case of this graph, we are not going to be using directed edges except for when we have self-referential edges. So what that means is this edge type goes from application to inventor. It does not need to be directed. We're not really, there is a hierarchy here technically, but we don't really care about it for the context of our queries. We want to be able to traverse this edge in either direction. So we'll leave it undirected. However, if we had an edge going from application to another application, we would want that to be directed, because otherwise there's no way of knowing, for example, in our schema, we have the parent application and child application. So there'd be no way to know which one's the starting point and which one's the ending point if it's not a directed edge. So we'll get to that, like I said, when we go through it in GSQL. But as far as you need to know, when you select directed, it also gives you the option to create a reverse edge, which just allows you to traverse backwards. You can only go forwards in traversal with a directed edge. So by creating that reverse edge, it allows you to traverse that reverse edge just in the opposite direction. Additionally, you can select the source and target vertex here. And there's this plus icon here where you could select multiple. So this is those compound edges that I was talking about. Obviously, this isn't going to make sense here because we only have 2 vertices, but if we had more vertices and we wanted this edge to be expressed between all of those different vertices, then we could keep adding them to this list. And then lastly, just like with our vertices, we have a field for attributes, and that looks exactly the same as what it did for vertices. So that is the basic process of clicking through this Graph Studio interface and creating a schema. It's really pretty simple. If anything, it is slightly tedious, but like I said, I find that when I'm first creating a graph, this is really the way to do it. So I can quickly and easily visualize those interactions and make sure that the things that I'm putting together make sense within what I'm trying to do. It's a little bit tougher to discern exactly what's going on when you look at the code, but we're going to get into that. So what you would do next here is you would click publish schema, and this would publish the schema to your TigerGraph server. When you create it through here, right now, all of this only exists within this UI. If I were to navigate away from this page and come back, it would all be gone. So, I mean, it'll warn you, if I go to refresh the page, it's going to say, hey, you might not want to do that. But if you want this to be permanently applied to your TigerGraph server, you will need to publish your schema. So let's take a look at what this looks like via code. So for that, I'm going to be using our notebook. So this is a continuation of the same notebook from last time. And this is just a Jupyter notebook. It will detail all of the same things that I've been talking about in this presentation, some of them in a little bit more detail, the whole process of going through all of that. But what we really care about is getting the our code. So when we create a vertex or when we create an edge in GSQL, it has a particular pattern to it, and that pattern is relatively easy to learn. So when we create an edge, we can see that we say when we create a vertex, we can say that we're creating a vertex. So that's all pretty self-explanatory, create vertex. Application, so this is the name of the vertex. We can see this following the pattern here. So we're giving it the vertex type name. And then additionally, we specify the primary ID, or we say that this is the primary ID. We tell it what the name of the primary ID is. So this is ID in this case, and what the type of it is. So that in this case was a string. And then after that, comma separated, we have a list of attribute name and attribute data type. And that will continue until we are done adding our attributes, where we close with a parenthesis to say application contains all of these attributes. And at the end, we have some with flags that we can set. You can read more about those in the documentation, but the one that we really care about now is the one that we had checked before, which is with primary ID as attribute equals true. So looking at this and then looking back at this here, you can see pretty much directly how everything maps up. There's our vertex type, there's the name of our primary ID and the type there, and here's our attribute with the name and the type as well. Oops. So you can see pretty much how those directly correspond to this data pattern here that our vertices follow. When creating an edge, it's going to look almost exactly the same. It's slightly different. So we'll have create, and then we have a specifier here as to whether or not it's a directed or undirected edge. Then we specify that it is an edge. So create undirected or directed edge. Then we have the name of the edge and its source and destination vertices. So we're saying this edge continuation type is going from application to the vertex type called continuation type. And additionally, if we had any attributes, then we would have them listed just like with our vertices as well, comma, attribute name, attribute data type. Additionally, here we have another with specifier that we can have after the edge. And this one we're using to specify that this one has a reverse edge. So this is a directed edge. You can only have a reverse edge on a directed edge. So that makes sense because otherwise an undirected edge doesn't have a direction. So it doesn't make sense for it to have a reverse. So when you have a directed edge, you have the ability to specify that you want to create a reverse edge, and then you can give that a name as well. And then once again, I just want to step into these compound edges again, because they are ever so slightly different, but it's good to know how to create them, and they have a slightly different way of loading data into them as well. So we'll take a look at that later on. But we will say again, create undirected edge in code. And then what we have here is pipe separated list of source and target vertices. So in code, for example, goes from an address to a postal code, goes from a correspondence to a postal code, and it goes from a city to a postal code. So those are the different areas where that edge can exist. And because of that, we just need to separate them by pipes. But otherwise, it looks almost exactly like our standard edge declaration. So you can see now kind of how you could write this all out by hand. Obviously, it makes sense. It has a pattern that it follows. You can see probably how it's easier to do this just clicking around through the interface, because as far as our schema goes, this is just the vertices and these are all of the edges. So you can imagine writing all of this out by hand, probably not the most fun thing. Luckily, I did all of this through the interface and just pulled this in by using that export functionality. So when you do export, you will end up with an export of your graph that contains a few files. Of those files, these are the three most important ones: DB export, global, and global schema change jobs. And if we just quickly poke around in them, we can see that these contain, global, for example, contains our entire vertex and edge declarations. And some of these as well contain our graph declaration, as well as these are our loading jobs, but we'll get to those later. So just goes to show anything you do through the interface, it is very easy to get this code out of it. So now to run GSQL code on our TigerGraph solution, there are a couple options that we can take. For the purpose of this demo, we'll be using TigerGraph. So this is just our Python connector. So we'll want to go ahead and install that. But otherwise, you can use the GSQL REST endpoint if you wanted to submit all of your GSQL code over a REST endpoint. You can use the GSQL terminal if you have access to the TigerGraph solution itself. You cannot do this with the free tier cloud instances, but any of the paid cloud instances, or if you're running it on-prem, you have the ability to just log into that GSQL terminal and automatically run that code. So we'll go ahead and install PyTigerGraph. And then down here, we'll need to connect to our TigerGraph solution. I go over this a bit more in our PyTigerGraph tutorial, so definitely follow that if you want a bit more in depth. But basically, we just have to specify the URL of our solution, the name of our graph, and our username and password in order to connect. So go ahead and run that. And we'll see that we've connected because down here, I'm just executing the GSQL ls command, which will list anything that's currently on our TigerGraph server, which should be nothing because I never published that schema and we started with a blank instance. So this will take a second just to establish our initial connection. And here we can see that we have no global vertices or edges. We have no graphs, we have no vertex types, and we have no jobs as well. So everything looks good from that standpoint. One thing though to note is that this is purely a connection to the TigerGraph solution. Remember how we have a solution and we have graphs within that solution. If we want to attach to a graph, we need a authenticated connection. Because graphs can contain data, if we want to actually be able to access that data to either add it, remove it, or view it, we need to make sure that we have permission to do that. So TigerGraph has the ability to assign different roles to different users. So for example, this TigerGraph user has all of the roles, so it can do pretty much whatever it wants. So what we're going to do is create a secret on our graph specifically. We're going to use that secret to create an auth token, and then we'll use that auth token to securely connect directly to that graph instead of the broader TigerGraph solution as a whole. Obviously you don't want, if you have a bunch of tenants using your graph, you don't want anyone just being able to create secrets and everything willy-nilly. So you have the ability to manage those roles to restrict who has the ability to create those secrets and hand out those tokens. But for us, we're the only user, so we get all the privileges. Then here, I'm just listing the vertex count of star. So any vertices in the graph, if there are any, we will print out the number and their type. But of course, this is an empty graph, so we don't have any. If I had clicked the publish schema button, we would need to remove that schema from our graph. So this is just a block of code which generates what's called a schema change job. And this will programmatically select any vertex types or edge types that are in your graph, create a schema change job, which will drop them from the graph and then execute that schema change job and then clear it from your graph as well, just so you start off with a blank graph. Additionally, we are going to drop the graph as well. So before we created everything, we created our schema within the graph space when we were clicking around in TigerGraph. So all of this is, remember, within our graph space. However, when we're doing things via GSQL, it's a little bit easier to work within that global context because any changes that you make to schema within a graph context have to be published as schema change jobs. However, when you're creating things within the global context, you can just create those vertices. So there's a little bit of a trade-off there for the two different approaches to doing that. Obviously, if you create your entire schema through the Graph Studio interface within the graph and then export that, then it will give you a schema change job, which will set up your graph schema. But for this case, we're going to be creating our schema at the global level and then importing it into our graph, or using all of the attributes from it to create our graph. So this big block here should look familiar. These are just the declarations of our vertices and edges, and we just have them within this connection.gsql block. So this is just for TigerGraph saying, hey, run this GSQL on the TigerGraph's solution that we have connected to. So I'm going to go ahead and click play there, and on the edges as well. And we're going to see these execute, and we'll get a confirmation message just listing all of the different vertex and edge types that have been created on our TigerGraph solution. So I'll just take a couple seconds to go through while it's doing that, see if there are any questions. Oh, that's not good. So let's see. What is going on here? Connected. Again. Huh, it's not like that. All right, we'll take a look at that and see what's going on there. But otherwise, this would create the schema within the graph. And if we were to head back to see if we can, well, we shouldn't be able to create the edges. Notice how we're creating the vertices here before the edges. The edges need the vertices to exist to have to know what they're pointing to and from. So because of that, we just create our vertices before our, oh yeah, looks like we're having an issue. So let's head back to our TigerGraph solution, see if we can quickly figure out what's going on. Otherwise, this is going to be a slightly less exciting demo. So here we have our patents graph. However, we're working within our global view. If we go to design schema, yeah, did not pull anything in. That's frustrating. Always breaks when you go to do the demo. Either way, we'll continue on. We'll pretend as if this had created our schema, and we can see from here what this would look like within the TigerGraph UI. So we would have all of that schema laid out, and we can see that there are these little globe icons representing that it was done in the global space. So down here, we would see that we create, I think I see what's going on. Just going to first drop that other graph that we'd created. There we go. Patents cannot be dropped. That's not good. So long story short, though, we would get the schema in here, and then we would have a separate patents graph, which would have that information in it as well. Let's try that one more time. And no, okay, it's not going to cooperate today. That's all right. Graph name is uppercase. Yes, here it would be. So we've already removed that. So this will still not work because there is no patents graph currently because we had deleted it through the interface. I'm not sure exactly what is going on here. All right, that's all right. So we would have our schema populated within the graph interface. And here we're using connection.gsql to create our graph using all of the elements of that global schema that created. So create graph, we're calling it patents. And then here we're going to list off all of the vertex types and edge types that we are going to use or bring into that graph. So what that will result us in is a graph called patent, which contains all of the elements of our global schema. And we can tell that they are elements of our global schema via the little globe icons that they have on them. So once we do have a new graph, we need to, again, because we dropped that old one, we created a new one, we'll just need to securely re-authenticate with it. So that's just the same block of code again, where we create our secret and use that to get our token. So now we're going to take a look at data mapping. So data mapping is, once we have our schema in, it's how we actually take our data files and we say which field goes into which attribute, which vertex ID type, and all of that sort of stuff within our graph. So because we unfortunately don't have the schema in place, I'm going to just quickly create some stand-in vertices for us. So that way we can do some basic mapping. I'm using Inventor just because we have a unique case here that we want to do with it. First name, middle name, last name. And we'll additionally tie these to an application. I'm aware that these aren't all of the attributes for our Inventor vertex type as defined by our schema from earlier. Just in the sake of getting through things quickly here, I'm not going to fill that completely out. So we'll create an application as well, just so we have something to link that to. And we will then create an edge between them. And we'll just call that as application. We'll go ahead, we'll publish the schema now, and this will actually get updated on the server. And if we refresh, we can see that it is still there for us. So what we'll want to do is head into the data mapping. We did this within the global view. That's all right. So we'll just select this. We'll bring it into a patents graph, create, and that will again spin up a patents graph for us. And then once we have that graph, we can look at the we'll take a look at what we look at. So now we have our graph up, and we'll see that our schema, once again, now we have those little globes indicating that these are part of the global schema, even though we are within our graph schema. And if we select this map data to graph tab, we'll see again, this new window will pop up, and we have again our schema here, but we also have this tab on the right. Now that's not really going to mean much until we start uploading some data. So we can upload data using this add data file button. You can click on that. That will just bring up this interface where we can choose our files. We can go from a file or an S3 bucket. We'll just be going from a file here. And this is these files that we created in the first half when we pared down our data set. So we're going to upload all of those files to our TigerGraph server. And that'll go relatively quickly because these are limited. These are only 10,000, the first 10,000 lines of each one of our files. But now that they're on the server, if we click on them, we can see that we have a little preview for our files. And up at the top, we have some options that we can select from the file format, whether it's just a raw text file or some sort of compressed file, the delimiter between the fields, the end of line character, the enclosing character, and whether or not it has a header. So all of these have headers, and a few of them have quotes as enclosing characters for some of the fields. So we can see that once we added that enclosing character, we had this stray column here. By adding that enclosing character, now we only have the columns that we're looking for. So for the entirety of this data set, we'll be doing double quotes as the enclosing character, and we will also have a header. Let's go ahead and add that in. So now let's look at what mapping that actually looks like. We'll use these crossed arrows here to start our data mapping. We can select our file, and then we can select one of our vertices. And what that will bring up on the right, and there are these 3 buttons here that allow you to adjust the size of each one of these panes. So I'm just going to do that to make this one a little bit bigger. But what that will bring up is the column titles of our data file, and then any of the aspects of what we are mapping it to. So here we're mapping it to our inventor Vertex. So we can see that our inventor Vertex has an ID, first name, middle name, and last name. And to map these up, we would just find inventor name last, inventor name last, inventor name middle, middle, first, first. And that's that basic mapping. But we can do some more advanced stuff here. We don't have to, but for this particular vertex, we don't have a unique identifier for person. So we could create one that's unique for each person, but then we miss out on the opportunity of what if the same person has submitted multiple patents, right? So we need a way to be able to link back a person to the patent or multiple patents that they've created, even though we don't have a unique identifier. So we need to create essentially a unique identifier. For this particular use case, we are going to make an assumption. And the assumption that we are going to make is that there are no 2 people in this data set who have the same first name, last name, and middle initial. It's a broad assumption. I know it might not work for all cases, but for the purpose of this demo, that's the assumption we're going to make. So therefore, we can create a unique ID by concatenating all of those together, first, middle, and last. Okay, let's do that. But the first thing I want to do before we do that is just take a quick look at some of our other data files, because we have some where we have names listed in, there we go, in a particular order. So our applications file, we can see that we have examiners here listed, and the order of these names is last, comma, first, space, middle initial. So if we can, we want to try and replicate that format across the primary ID of our inventors, just so it matches the rest of our data set. So in order to do that, we will use some of our what are called token functions within TigerGraph. So you just click this little Sigma icon up here, and that will allow you to take a look at our token functions. So these are all sorts of things like concatenating together fields, changing the case or type of certain variables, and whatnot. So we're going to use GSQL concat. And then for our input parameter number, we're going to pick 5. And I'll explain why 5 in a second, because you might be saying there's only first, middle, and last. So why do we need 5? Well, the thing that we need to remember is we also need that comma and we need that space, right? We need first or last, comma, first, space, middle. So let's take a look at how we do this. We'll first take our last name, because that's what we're starting with. So last name, we'll link to input 0. So that's our last name. Now we need a comma. We need that comma before we put our first name. So we don't really have a comma data field here. So how are we going to do that? Well, by double clicking on this input, we can set it as a constant value. So here I can just put in comma, and now we have a comma. So last, comma, and then we can take first, and then we have a space, and we can just enter in a space, and then we can map our middle initial. So this concatenation is going to result in last name, comma, first name, space, middle initial, and we're going to take that output and map it to the primary ID of our inventor vertex. So now anytime that we load in a row from this data set, we will generate essentially a unique primary ID for that vertex. So that's sort of what a basic vertex, well, not quite basic, but what a vertex mapping looks like with a token function. When mapping an edge, it's very similar. So we just select our data file, we select the edge itself, and then we can do that same mapping. For inventor here, because we are constructing that primary ID as a result of fields from the data file, we're going to need to include that token function anytime that we want to access that primary ID of inventor, because it's something that we're generating. So to do that, we'll once again need to just bring in our token function. We can quickly set it up because we've done this before, comma, space, and we can map these things together. You might be seeing now how this is something that would definitely be a little bit easier if we had the ability to copy and paste code rather than having to click through this multiple times, but we'll get to that, don't worry. And then we can map that to our source vertex of inventor. And then application, the primary ID for our application vertex is this application number, so we can just directly link that. So what this will do is it will create an edge from an application vertex with this vertex ID to an inventor vertex with this constructed vertex ID. Now, something I just want to say here. An edge cannot exist without a source and a destination vertex. Makes sense. So if we map an edge and we don't map a destination vertex, so for example, here with application, we're going to, this isn't the case in our actual schema, but for this demo, we're going to talk about this. This application vertex, if you recall, has no attributes. When I created it earlier, it has no attributes. It just has the primary ID. So because of that, all we need to create a vertex is a primary ID. You know, it's the only part of the vertex that is required to be unique. So if we go to create an edge and there's no application vertex that's been mapped, you know, we don't have an arrow here mapping to an application vertex, then we're going to create an application vertex with this primary ID. If that application vertex had any attributes, well, we don't have the values for the attributes of the application vertex. You know, we're not working with the application file, we're working with the inventor's file. So what would happen is we would create that vertex with just the primary ID, and any of the attributes would assume their default value because we don't have values for them and we can't have nulls. And then what could happen later on is if we did map application and we had those values for it, and we went to load in that data, it would say, hey, an application vertex with that ID already exists. However, it doesn't have values for any of the attributes. So we'll keep that vertex in place and we'll just load in those new attribute values in place on the vertex that already exists. But what I'm getting at here is what's actually a little trick that we can use, right? So normally we would have to do this. We'd have to say, do that, and then application number and ID. But this is useless. Remember how I said before, all we need in order to create a vertex is the primary ID? Well, there's no sense in just mapping this primary ID when we already have the primary ID mapped from this linking to the edge. You know, we're already creating a application vertex with a primary ID, and because we have no attributes, there's no other additional information that we need. So we can get away with just mapping application via this one edge mapping, because it will create the application vertices with that unique ID, and there's no attributes or any other things to populate. So we therefore don't need to map directly to that application vertex, because those application vertices will be created when the edges referencing them are created as well. So that's just a little shortcut you can take to help prevent you from having to overdo your mapping. But like I said, this only works with vertices that do not have attributes. Those attributes, like I said, will not be loaded in. So if you have attributes, you will need to manually map to that vertex, but otherwise you just need to map to an edge. So that's what this looks like within Graph Studio. Let's take a look at what it looks like in GSQL. So we'll head back over to our notebook. And we can see that this is what a data mapping looks like in GSQL. That looks a little complicated, but we'll break it down really quickly. So first, create loading job. That's self-explanatory. We're creating a loading job to load in our data. We're going to give it a name, loading job name, in this case, load all investors. We're going to specify which graph it is loading the data for. For graph, for example, this will be patents. Next up, we define a variable for the file name. So here we're just going to call it my data source. Define file name, my data source. That just means that whenever we reference the file that we're loading in within the context of this loading job, we'll be calling it my data source. You could load in multiple files in one loading job. You would just need multiple variables for those different files. And then lastly, we have what is actually the meat and potatoes of the loading job, which is the bit that we just did through the interface. And we'll see here, load my data source. So load the file that we're trying to load to the Vertex inventor. That's that Vertex that we created and what we're trying to populate on it. Values is the values that we're loading in. I'll pick one of these edges just because we'll get to the concatenation, or actually concatenations in all of them. So here we specify that we're using a token function. That's our GSQL concat. So we have GSQL concat, that function opens up, and we have each one of those inputs to that function. Now you're going to be looking at these and you're going to say, what is $1? What is $3? Those are the numbers of the columns in our source data file. So if we go back to, we can easily see this through here. So right here, application number, this is column 0. This is column 1, column 2, column 3, and so on. So we can see that within here, we are taking column 1, comma, column 3, space, column 2. And if we look back at our file, column 0, column 1, comma, column 3, or yep, space, column 2. So we can see just how that is represented across our data file to our mapping. And then additionally, after that, any of the attributes of that vertex. So our inventor vertex had first, middle, and last name. So first, middle, last name. So we're just specifying which columns go to which attributes and IDs within a particular vertex. And then here we have using separator, comma, header, false, this should actually be true, end of line, backslash n, and quote character. So that's just showing us what we picked before when we were setting up those data files. That's exactly the same inputs that we had here, just expressed via code. So this one shows the mapping from the file. It shows it mapping to a vertex, and then it shows it mapping to each one of the edges. So for each file, we'll end up with a loading job that specifies how the fields from that file will be split across the different vertices and edges that we're mapping it to. And this is what all of our loading jobs look like. I would run this, but unfortunately, because we don't have any vertices or edges with these corresponding values loaded into our graph currently, this job would fail to run. But if it didn't fail to run, it would create a bunch of loading jobs with those mappings very similar or exactly the same as what we did through this interface. So then lastly, let me just make sure I got everything here. I guess I could have used this to better describe that stuff, but just going through what that looks like, those mappings, and how we do that. Obviously, the PowerPoint is the very condensed version of this. If you really want the depth, read through the notebook. It goes into a lot more detail even than I'm going into with this presentation. But we will head back to our file here. So to actually load the data through the Graph Studio interface, that's pretty simple. So we would, again, we have a publish button. All of this is only within the context of the web UI right now. So publishing it, we'll publish it to the TigerGraph server. And then going into the load data tab will show us that actual mapping. We can click this play button to load in all of our data at once. Or if we want to load in an individual file at a time, we can select that file and then select the play button to just load in that file. Doing it via GSQL looks a little different. So here is a little bit of a Python function where we specify the file that we'll be loading. So in this notebook, we have a folder called processed data. and that contains all of these smaller data files that we created. So we're just going to be pointing to that process data folder and then our actual data file. So this is pointing to a file on the system that you are executing the GSQL from. And then we are going to run our TigerGraph function of upload file. We're going to specify which file that is. So that's just the one that we mapped to up here. The file tag is the name that we gave to our file name. So for all of these, it's going to be my data source. So file tag is my data source. And then the job name is, again, just the name of the loading job. Load transactions, or load all inventors to better show the example, and then load all inventors down here. Obviously, creating a block of code like this for each file that you're trying to load in is a little tedious. So what I've done is just created a list of tuples of the file path and the name of the loading job. And then we're just going to have a function here, which will iterate through those tuples and load in each one of our files with their corresponding file path. And what we would see from that, once we had all of our data loaded in, we'd be able to return the vertex count of each of our different types of vertices, and we would be able to see how many of each type of vertex that we had actually loaded into the graph. So now you're going to say, okay, file location, we had 10,000 rows, but there's only 14 file locations. Well, that's right. That's just within our data set. Any of those rows, because they didn't all have unique file locations, any non-unique file locations will just be the same vertex loaded in. It will just create an edge between them. So we may have a bunch of, where's the applications one? We may have a bunch of applications that all point to a file location. It's just there are only 14 possible file locations. So they're going to share a bunch of edges with these applications as well. So yeah, that is really the basics of it. So from here, you would have your first 10,000 rows loaded in. And what you'd want to do now is start actually exploring your graph. Fortunately, we don't have any data loaded in, so this is kind of a moot point. We're out of time anyway, but you would go through here. You would select, for example, 5 random applications. You'd click on them. Let's just load this in quickly just so we have something. You'd click around through them, and you'd be able to see if it looks like your schema is working out, if your data mappings are correct, if all of your linkages look like they do. So that's why we're starting with these small files, is because if there are any mistakes, it's a lot easier for us to modify our graph when we have small amounts of data in it and reload those files than it would be if we waited 3 or 4 hours to upload 50 gigs of our full data set. We loaded it in, which would take more time to then load it in, and we find out that our date time in one of our files is in the wrong format, and therefore it's assumed all default values in TigerGraph, and now we need to modify that file, re-upload it to our server, and reload all of our data. It's a lot easier to do that with these much smaller starter files than it is with the entirety of our data set. So that's just why we're doing this. After I verified that everything worked with these 10K files, I would probably spin up a batch of 100K line files, load those in just to make sure there aren't any additional outliers that I missed from that small initial subset. And then from there, I would probably progress onto my full data set. Yeah, so what I would do after I loaded it in is I would pick some applications or some whatever I think my source vertex is, and I would start sort of clicking around to verify that there were actual connections and that everything was looking as we thought it would. So with our person, we can see that we are generating, in fact, the correct ID. So we have last name, comma, first name, space, middle initial. So that all looks good. And we can see already that we have a person who had 2 applications linked to them. So we've already created those graph connections, and we can verify now that creating that unique identifier worked out because we can see that that person has been linked to multiple patents. So we can already see those graph connections. So yeah, sorry that I wasn't able to show what was going on with all of our data loaded in. I'm going to try and figure that out, what's going on with that, and we'll push an update to the notebook if it was in fact an issue with the notebook. But otherwise, you could just follow along with all these steps and you would have a fully populated graph with all of your slimmed down files. And then all you would have to do in order to load in all of your data is just change the location of these files and run this loading job again. So if you created 100K files, you just do that. and you run your loading job again. And now you've loaded in 100,000 lines from each file, and you can start verifying your mapping there. And you can just see how easy it would be to step up to your full data set once you already have this code pipeline in place. So I'm aware I'm over time. I'm going to look through questions really quickly and try and answer those. If anyone has any questions, feel free to ask them now, and I will try and get to them as I can. Here's a great one. Terminology of the word type. Vertex type and edge type are the same as vertex and edge. They are not. So a vertex type represents something within our schema where we can have, each one of these is an application vertex, but they are both vertex type application. So vertex type represents the hierarchy saying, this describes what an application vertex will look like. So that has that schema information. I'll use Inventor just because we have actual schema. So Inventor vertex type says we have these attributes and this is our primary ID, versus Inventor vertex says this is one particular instance of an inventor and these are the exact values that that one instance has. So whenever I'm using type, I'm describing schema, and whenever I'm using vertex, I'm describing an actual row from our data file that has been loaded in as a vertex. So that's the distinction there, and kind of why I referred to those differently. Could I assist with some sample GSQL queries? That is the next session. We'll be writing queries for this. Can very large files be loaded? Yes, they can. Our data set, one of our files is 14 gigs. I don't know if that's your definition of very large, but yes, there's not really a size limit to the files that can be loaded. There are different methods though, which you might take to load those files faster. When I loaded this, so I do have one, actually, let me start this up really quickly. Apologies for this going over time, but this is the full pattern graph on a non-free solution with all of the 50 gigs of data loaded in and over 1 billion unique edges connecting all of our different data types. So we can poke around in there and just see quickly what that looks like. But there really isn't a limitation. There are, though, better methods than necessarily going through this interface. Loading files in parallel is possible, and we do have some notes on that in our documentation as well. So yeah, that kind of follows along with that bulk load as well. We can load multiple files in parallel. It's not doing that by default through the interface, but that is an option that you can specify when you are loading in your data. So yeah, unless there are any other questions, can loading be done incrementally, i.e. a new month? Yes. So you could set up something like a cron job to pick up a file on your server and load that in. If you have a Kafka stream, you could load in data in real time as it arrives at the TigerGraph server. There are plenty of different ways in which you can structure your data loads to allow you to load data as much or as little at a time as you would like. How do you delete data? Great question. So there's a couple different ways to do that. My personal favorite way is via a query, where I would just say something like delete data. And that query would have me select all of our data. So I'd say all equals all. So all is just a signifier for all, any, I think is what I want. There we go. And then I would say result equals select a from all a, and then I would do a post accum delete a. So what this will do is it will select every single vertex in the graph, and then it will iterate through every single vertex and delete them. And because we can't have an edge that doesn't point to any vertices, if you delete all of the vertices, all of the edges will also disappear. You could specify, of course, using things that we'll talk about in the next session, exact edges, edge types, or vertex types that you want to delete. But in general, this will delete all of it. there is also some notes in our documentation of functions that you can use to remove all of the data from a graph as well. I believe I might have one written down in this notebook. So drop all will drop all graphs and everything. You probably don't want that, but you can drop, I believe it's drop data store for, I'm not gonna misrepresent anything here. Our documentation does say how you can remove all data from a graph. It is a GSQL command. I just don't know it off the top of my head. But yeah, really quickly, just because I did tease it, we'll take a look at that large graph, which does have everything loaded into it. So we can just quickly explore that. What we can see if we go to the Explore Graph tab, once we select our graph, we could select some applications. Will take a sec. Like I said, it is a large graph. And I did just spin it up, so it is in the process still of loading everything up because I did just start it from asleep. So this may take a second to run, but we would be able to see the entirety of what is loaded in here. And we'll be looking at how we can query that in a couple weeks. So yeah, if anyone wants to stick around for a minute just to see this, feel free. Otherwise, this is kind of the end of the educational content here. Thank you everyone for putting up with me going over time, and for whatever reason that notebook entry not really wanting to load in our schema. Like I said, I will take a look at that. Of course, it always works when you practice, but not when it comes to the real one. So I think that that's just some sort of misformat issue, either with my command or something with the state that the TigerGraph server was in at the time. Yeah, so this is still spinning up. And we can see that again, I'll just poke through this really quickly, but this net data tab here on our TigerGraph solution, no longer will allow me to connect. But the net data tab allows you to see, it's basically a performance monitor for your TigerGraph solution. So if we were to be able to open that right now, we would see a steadily inclining slope in how much RAM and CPU we are using as it's bringing all of our data back into RAM as the TigerGraph solution is spinning up. So that's just why we weren't able to quickly do this right now, because it is still bringing itself up. So it's going to be a little bit sluggish for the first couple minutes as it gets itself set up. Yeah, so like I said, it's a shame that that's taken a minute. This is some of the issues with bigger graphs. And normally, if you had a production use case, you wouldn't be stopping and starting your graph frequently. So this is not something that you would have to worry about. However, the graph is too big to fit on a free tier solution. And I don't want this thing sucking up money when I'm not using it. So that's why I shut it down when I'm not. And why we have to go through this process of waiting for it to spin up. But this is not something that you would normally need to worry about in a production basis. It's taking its time. Well, either way, maybe I'll leave this as a cliffhanger for next time, and we'll start off by taking a look around this big graph and then exploring what those queries look like. And here we go. So here we have some of our patents, or our applications rather. We can see that they actually have data loaded in them because all of the mappings were completed and successfully done for this graph. And if we double click on any of these, it will expand out all of the vertices connected to them. And we can see that a lot of these are attorneys. Look at that. So there's a bunch of attorneys attached to that. These are the different codes attached to the events related to the graph. Continuation type. Here is our inventor. So we can see if this inventor has been on any other applications. They haven't, but we can see that they are located in Great Britain. And they filed, they did file another application as well. So we can open those up. And now, using the power of graph, we'll be able to see if there are any similarities between those two applications. So if we separate this out, we can see that there are actually a lot of similarities between these two applications because they share a lot of the same vertices. So for example, they all have the same attorneys on them, and they follow with under the same continuation. Okay, so that makes sense. So this is one of these applications is a continuation of the other application, as we can see by them sharing the continuation type. And that is additionally why they share all of these attorneys and other vertices as well. So already just by clicking around, you can see the power of some of the things that we can see through graph, but obviously next time we will get into actual things that we can do through queries and some of the really cool advanced analytics that can be done via those GSQL queries. What is the desired memory to disk percentage? That's actually a great question. So the only aspects of your graph that are being loaded into memory are those primary IDs of your vertices and any indices that you create as well. So you do not need as much RAM as you have data. However, it's best to have overhead because when you do run queries, you can use up RAM for variables within those queries. So if I write a query, for example, the one that we wrote here, that's going to go over, oops, that was the other graph. Here, that goes over every single vertex in the graph. Well, we're going to need to store those vertices in memory for the purpose of the query. So we're going to need at least as much RAM as we had to hold those in the first place. I'm misrepresenting it. There is plenty of optimization that's done under the hood to help optimize that process. But personally, I would try to look at, take your data size, divide it by 5, and multiply it by 3. So we have 50 gigs. So we'd want at least 15 to 16 gigs of RAM on our TigerGraph server, just to be able to store all of that and to be able to query it efficiently. I believe that this one that I have set up is 64 gigs of RAM. It's a bit potentially overkill, but it will allow us to handle those complex queries. And then disk size, as far as disk size, you really only need disk to store your data, the actual data files. So for example, the free solution is limited to 50 gigs and our data size is 50 gigs. So we would be able to load in all of that data because it's just going to, the data files are really all that's stored on the disk. And then eventually the graph, once the data store, once the graph is shut down or just in the background, it also stores that information on disk, but that is highly compressed. So it takes up a lot less space. So yeah, that's the poking around. That is the exploring the schema, and that is the slight tease of what this full graph looks like. So I hope that you're looking forward to, yeah, here's some big numbers. So I hope that you're looking forward to next session when we can get into querying and maybe see if I can fit one of these within the hour-long time limit. So thank you all for attending. Thank you all for sticking around. And I hope that you learned something, enjoyed, and that you're looking forward to trying out TigerGraph on your own. And as usual, we're more than happy to answer any questions. So through our link sheet, feel free to get in contact with us through Discord or our community forum, where we're more than happy to answer any questions that you might have. So thank you all. And for this time, for real now, I'm signing off. So thank you all for attending, and I hope that you enjoyed.